We ended up last time with me asking you what would be the kinetic energy of a proton traveling 2/3 of the speed of light. And this is hopefully what you should have come up with for that. And this is the classical Newtonian way to calculate kinetic energy. So based on this very, very small number of joules of kinetic energy of a proton going 2/3 of the speed of light, my question is, how on earth could a proton end up with so much kinetic energy that it had 50 joules worth of kinetic energy, which is what the oh my god particle had? And to answer this question, we have to understand that when objects move close to the speed of light, everything changes. So at first you were taught the speed of light is constant. Light always goes 3 times 10 to the 8th meters per second. And it never changes. And nothing can go faster than light. But then we saw that the speed of light indeed does change depending on what medium the light is going through. We saw that its speed decreases in glass compared to air. The speed of light is actually very slightly bit slower in air compared to a vacuum. And so then you were left with, what's the big deal? They say the speed of light is this very specific constant, and it always stays the same, but what we're talking about with the speed of light being a constant is that when an object is going near the speed of light remains the same for all observers, and everything else changes. So here's you driving around in your spaceship, and you are a law-abiding citizen, and you are going at 0.9 times the speed of light, the universal speed limit. And here's a space policeman with a siren here on top of his spaceship, and he clocks your speed and he measures 0.9 times the speed of light. But at about the same time he's clocking you, there's a crazy person who's flying by you, passing you, and you measure his speed from your spaceship to be also 0.9 times the speed of light relative to you. And you think to yourself, oh heck yeah, there's a police officer right there, he's going to get nabbed. But that police officer isn't going to measure 0.9c plus 0.9c for this guy like we'd expect. We'd expect the policeman to measure the spaceship going 1.8 times the speed of light, which is above the universal speed limit. But in fact, the space police guy does not measure velocity relative to the space police ship of more than 1 times the speed of light. So he might actually measure somewhere in the region of like 0.98 or 0.99-ish times the speed of light, and we'll see the equation for that a little bit later. Let's think about another situation. We're here on the Earth, and there is a spacecraft going by at close to the speed of light. So at 1 second, the spaceship is here, and the next second, it's all the way over here. Figures not drawn to scale. On this spaceship is a photon flare gun. Photon flare guns may not be real, I think I just made that up. That fires one photon from one side of the ship to the other side of the ship, and it hits the mirror over here, and it comes back, and it's detected on the same side of the ship where it was emanated from. And the path of the photon that I've written is its path over 1 second as seen from those inside the ship. People cruising inside the spaceship going near the speed of light are going to see that photon, just one photon of light, travel the distance d and then back again. So the distance traveled is 2d. The time it takes, we said, is 1 second. But this event would look completely different to a stationary observer on Earth. So the people on Earth see this photon released on the traveling ship, and they see it move with the ship as the ship progresses. So when half of that second is over, that photon has traveled across the ship and it's hitting the mirror. And at that half-second point, the ship is actually about here. And the people on Earth see that photon reflect off the mirror as the ship is at its halfway point, and they see that photon continuing to move with the ship as it comes back to the first side, and the ship has finished its travels over that whole 1 second period. So let's make that a little more clear. This is the path of the photon observed by somebody on Earth, a stationary observer. And clearly, to someone on Earth, it looks like that one photon, that same photon, has traveled a lot farther than it appears that it traveled to the people in the ship. And if we wanted to use trigonometry, we could make a triangle like this. We could call the distance there d. We could, this is still d, this side over here, we could call this angle theta. And from that trigonomic identity, we could get sine theta equals little d over big D, solve for big D. And to someone on Earth, we'd have a new delta x, which would be 2 times big D, which is 2 times little d over sine theta, in what to the people on Earth seems to be a 1 second time period. Now we've got ourselves into a big pickle. There seems to be a contradiction here. If the people on the ship measure the speed of light, remember velocity is delta x over delta t, change in position per change in time, they're going to have a different delta x than the people on Earth who are measuring. And they're going to get a different velocity that they measure for the speed of light than the people on Earth. And this is where the constancy of the speed of light comes in. The speed of light is actually the same for both observers, but everything else changes. Other things change. For example, time. Things that don't seem possible that would be measured differently by 2 different observers end up being different. So in this case, it's actually the passage of time that's experienced differently by the observer in the ship and the observer on the Earth. So for the people on Earth to measure at the same velocity of light, if the light looks to them to be traveling a greater distance, the people on Earth are going to have to experience a greater passage of time also than just that 1 second. That ratio of time that the Earthman experiences compared to the spaceman is equal to the Lorentz factor, and that is written as gamma. And here's what gamma is, this Lorentz factor. It's 1 over the square root of 1 minus the velocity squared of whatever is moving, and that is divided by the speed of light squared. Why don't we just write this? Well, it's because this Lorentz factor shows up a lot in relativity. I said everything changes. Everything changes by a factor of the Lorentz factor. Now, it doesn't seem to make a lot of sense that someone on Earth would experience significantly more time passage than someone in a spaceship. I'm just going to say this is time for somebody going at a fast velocity, somewhere close to the speed of light. It seems quite weird that one observer would measure a time passage of, say, 10 seconds, while the other would measure a time passage of, say, 25 seconds. But we know this has to be the case because it would make less sense for the laws of physics to be different depending on how fast one is going. It's established that the laws of physics hold for any observer who is in any inertial reference frame. All that means is that that observer is going at a constant velocity. For example, if someone on Earth were to measure a blue photon of light and measure its velocity, they would find that it's going exactly the speed of light. If someone whizzing by Earth at 0.8 times the speed of light in a spaceship were to measure that same blue photon and measure how fast it was going, they would also find that it was going exactly the speed of light relative to their spaceship, even though their spaceship is going almost the speed of light relative to stationary observers on the Earth. And even somebody in a spaceship buzzing the other way at very high speeds, they'd still measure the same photon, even though it's coming at them, to be going the speed of light. So everybody, so long as they're not accelerating, everybody here is in an inertial reference frame. People who are not in inertial reference frames are accelerating. So, for example, a ship that is blasting off from the Earth and accelerating faster and faster, trying to get out of the Earth's atmosphere, this is a non-inertial reference frame because the acceleration is non-zero. So we've seen that in order for this constancy of the speed of light to hold, in order for all observers to measure the speed of light to be 3 times 10 to the 8th meters per second, time must pass differently for different observers. Also, the length of a speeding object is measured to be shorter for somebody who's watching that object whiz by than for somebody who would measure the length of that object who was traveling in the object. So that speeding spaceship would look like this to the people in the spaceship, and they'd be like, oh, we are L meters long. But to a stationary observer, that ship would look all smushed and contracted, and a stationary observer from the Earth, say, would be like, oh, that spaceship is clearly L over the Lorentz factor meters long. And it's not just length that gets changed, also mass. A observer who watches a particle fly by will measure that mass to be multiplied by the gamma, the Lorentz factor. So this is called the relativistic mass. And this applies to anything that's approaching the speed of light. And just to clarify, even if you're just walking across the room, there is some amount of change due to relativistic effects. But until you get going really fast, that change is just so small that it's negligible. If you were to graph the Lorentz factor, you would see that it's exponentially increases as v gets higher, as the velocity gets higher. So it starts out very low and flat and then sharply rises as velocity approaches the speed of light. So it's somewhere in here where the Lorentz factor becomes high enough that there's a significant difference between relativistic mass and normal mass, and when there's a significant time dilation, length contraction, etc. And I want to make sure I measure or label my axis here. This is the Lorentz factor on the y-axis. Now let's think back to that proton, the oh my god particle, the proton that was measured to have 50 joules of energy. It must have been going very, very, very close to the speed of light. Relativistic effects must have made its mass much, much larger than that of a normal proton. And as you get closer and closer to the speed of light, the Lorentz factor just keeps going up. It just increases more and more steeply, just exponentially getting larger. So this must have been a very heavy proton, because this oh my god proton that had 50 joules of energy was going just femtometers per second less than the speed of light. And let me just remind you of the metric prefixes. Milli is small, micro is smaller, nano is nano, then you go pico, then you go femto. So if we were to calculate the energy of that proton while incorporating relativistic effects, we would have had to assume its mass was gamma, the Lorentz factor, times the normal mass of a proton, times the velocity squared. And when we do that, then there's really there's no limit to how energetic, to how much kinetic energy anything can have, so long as it has some mass. If we were to plot the kinetic energy of something versus its velocity, we would see that that curve steeply rises as you get close to the speed of light, and it just keeps going steeper and steeper up, just like the Lorentz factor. And the kinetic energy of an object would actually have to get to infinity before that object would reach the speed of light. And that has a lot to do with why the speed of light is the universal speed limit. And that has significant implications on space travel, because as you could see here, the closer you get to the speed of light, the more energy it takes to accelerate something. When you get into relativistic speeds, every meter per second that you want to add to your spaceship in terms of its velocity costs you more and more energy. That about wraps it up for me today. Now that you've watched this video, go watch an even better video. Go watch Interstellar. There is some very accurate physics in there about how time dilation also occurs near gravitational bodies, such as black holes.
Made with Doodlecast Pro.